Welcome back, and in this video we're going to be looking at the evidence for the electron structure. We're going to be focusing on one key piece of evidence, and that is the ionization energies. We're going to look at both successive ionization energies and how the ionization energy changes going across and down the periodic table. So we're on page 10 of your notes and we're looking at this ionization. So this is where an atom loses one or more electrons. Now that process requires energy. It is an endothermic reaction because it requires energy to pull the electron away from the nucleus. Now the process depends on three things: the distance between the electron you're trying to remove and the positive nucleus, the number of protons in the nucleus, and the amount of shielding that's provided by complete inner shells of electrons. So the reaction is written like this for an ionization energy of an element. So I've got my element in its gaseous state and it's having one electron removed to become a positively charged ion. And we call this the first ionization energy. So we define the first ionization energy as the energy required, and it's always required because it's an endothermic reaction, to remove 1 mole of electrons from 1 mole of gaseous atoms. So there are kind of some key things that you need to get into your definition. It's always energy required, it's always 1 mole, and it's always from gaseous atoms. And I have here the first ionization energy of sodium. So I have sodium gaseous atoms forming sodium gaseous ions and losing an electron. Now the second ionization energy of sodium is the energy required to remove the second electron. So this time I'm starting with the 1 positive ion and I'm removing the second electron. So basically I can then keep doing this. I can keep removing electrons from increasingly more positively charged ions. And I can keep doing this until I run out of electrons. So the number of ionization energies an element can have is dependent on the number of electrons there are to remove. One thing to notice, be careful, this is from free gaseous atoms, not molecules. So you're starting, for example, from H, not H2 or half H2. So I'm writing out the two equations to represent the stages of ionization of magnesium atoms to form the cation. So I start with a magnesium gaseous atom and it becomes a magnesium gaseous 1+ ion and it's lost an electron. Then for the second one I start with the positively charged ion and I go to the 2+ and my electron. And you should notice that the second ionization energy is greater than the first. The reason for that is in this case I'm removing an electron from a neutral atom, but here I'm trying to remove an electron from a positively charged ion. So it's going to take more energy to do that. So basically removing an electron from a positive ion takes more energy than removing it from the neutral. So as we go as we remove more electrons, it becomes harder and harder to remove the electrons because we're removing them from an increasingly more positively charged ion. Now if you look at the numbers here, we have a jump between 738 and 1451. So roughly doubled. Now if we compare that with sodium, now if we look at the first two ionization energies of sodium, we see there's a much bigger jump between the first and the second. And this is our first piece of evidence that we have these principal quantum shells. So let's think about the electron structure of both of these. And I'm just going to use dot cross diagrams for sodium and for magnesium. So sodium has 2 electrons in its first shell, and then it has 8, and then it has 1 in its third principal quantum shell. Magnesium again has 2 electrons in the first, 8 electrons in the second, and 2 electrons in the third. Now, the first ionization energy of sodium, we remove this electron here. So this electron is removed. This electron here is removed. So we have our first ionization energy, sodium, gaseous, going to sodium plus iron, and it's lost that electron. Now the next electron that we're going to try and remove has to come from a principal quantum shell closer to the nucleus. So this, or one of these electrons, is the next one I'm trying to remove. And because it's closer to the nucleus, and it's lost a layer of what we call shielding, because this electron was shielded by this inner shell of electrons, it's much harder to do. Whereas for magnesium, first ionization energy, I lose this one. Second, I lose this one. I'm removing both electrons from the same principal quantum shell. So they're the similar distance from the nucleus, and they've got the same amount of shielding. So although it does increase, it's not a big jump. However, if you looked at the third ionization energy of magnesium, you would see that is where the big jump would come in. So to remove that second electron from sodium ion requires a huge amount of energy. Remember, this is always an endothermic reaction. We get the energy back by forming ionic bonds, but that amount of energy is so large it would not be compensated for by the ionic bond that could be formed. However, the second ionization energy of magnesium only requires a much smaller amount of energy compared to sodium. And that would be provided by the ionic bond that could be formed with magnesium 2+ ion. If you look for the next example at aluminium, we have a steady increase as we go from the first to the second to the third ionization energies, and then we have this large jump. The reason for this is aluminium has 3 electrons in its outer shell. So it's a gradual increase as we're removing an electron from an increasingly more positively charged ion, but then there's a large jump to remove that 4th electron, because we're removing an electron from a shell which is closer to the nucleus. So aluminium can form both ionic and covalent compounds. And the reason for this is related back again to this ionization energies. So to remove the first 3 electrons, it does require quite a large amount of energy. And in some cases, that's not compensated for by forming the ionic lattice. So in some cases, sharing electrons, in other words covalent bonding, is much more energetically favourable. So if we move on to look at potassium and compare it with sodium, you would expect the first ionization energy of potassium to be lower than that of sodium. And you would expect its second ionization energy to be approximately 10 times its first. And if we look up the values, we find that potassium is plus 419, but its second is over 3000. So the first ionization energy is lower than that of sodium because potassium is a larger atom, it's lower down in the periodic table, it's got more shielding, and its outer shell electron is in a shell further away from the nucleus. If we look at that definition of the second ionization energy, there's an equation to show it for potassium. Do remember, it's not to remove 2 moles of electrons, but to remove the second electron. So it's the energy required to remove 1 mole of electrons from 1 mole of gaseous 1+ ions. So when you do a flame test on an element or ion, you get specific lines in its emission spectra. And what these lines represent is they represent the energy being given out as the electron drops back from a higher energy level to a lower energy level. And they're only at specific frequencies. That's because there are specific gaps between the energy levels that correspond to these frequencies.
Absorption lines are the same idea and they match the emissions line. It's just here we're looking at what energy is being absorbed by my element or ion. And these absorption and emission spectrum can help us identify which elements are present, even if those elements are a long way away. So for example, we can look at the spectra of the Sun and we can determine which elements are present in the Sun. So that finishes this little video just looking at ionization energies. In the next video, we're going to be looking at successive ionization energies, that's taking one electron away from a particular atom. We're also going to look at first ionization energies as we go down a group and across a period. So until then, take care, stay safe, bye bye.